Okay, and everyone, this is Professor Lai. Welcome back. So this video is chapter 6 video part 2. Alright, so you may still remember that actually in the part 1 of our chapter 6 video, alright, we already talked about some general concepts within the manufacturing process, and I also introduced a new quantitative methods, alright, basically called a little store in order to quantify the working process inventory within the whole manufacturing process, okay, which is actually very important. All right. So in the part 2 of our chapter 6 video, we will continue to talk about, the production process within the whole manufacturing procedure. All right. And we will talk about and also compare different type of production processes, and also I will continue to introduce another quantitative method, especially within the assembly line production procedure. All right. So let's start from the production process. The different types itself. All right. So I think all of you guys should already look at the textbook. Actually, the textbook already shows a very detailed and clear explanation about each different type of production processes. All right. So here in this slide, I basically show the definition about different type of the production process that we generally classify, and yeah, and I do require every one of you to go back to the textbook and look at the some example and also definition and also the comparison among different types. All right, here I will lead you guys to briefly go through those different types and also compare among different types. All right. So as you can see, in general, for the production process, we separate into these five different, classification. All right. So which are project production process, work center production process, manufacturing cell production process, assembly line production process, or a continuous process. All right. The name is just called continuous process. All right. So here basically this is the definition of every type. All right. So uh, I think basically the production process for every type is very clear. All right. But the key point here is that what is the main difference? All right, among those different production process, and what kind of product is more fitting for what type of the production process? That's the main thing that we want to figure it out. All right. So let's first look at the project. So the project production process basically the product itself will remain in a fixed location. All right, and the equipment can be easily moved to the products. All right, so just based on this definition, you can already feel that basically for this type of the production process, everything is focusing on the project itself, right? No matter it's the facility, no matter it's the equipment, no matter it's let's say the employee or laborers, everything is focusing on this project. All right, so you can see that basically this manufacturing process itself is not standardized, right? On the opposite side, actually this is more customized, right? Because actually we're dealing with a specific project, and we wanna, although we are doing the manufacturing process, but the first task that we want to reach basically is to finish this project, is to complete this project successfully. All right. That's why for this type of production process it actually has a low level of standardization procedure, but with a very high customization process. All right. So that's a key point for project type of production process. All right. And then the work center type of production process. Okay. Work center type of production process is a little bit different. All right. And you can see that basically the work center in those type of the production process, all right, we put similar equipment or functions or facilities together as a group, all right, and every work center will basically do their job, and they may coordinate with each other, all right, yeah, very frequently, and although the coordination, the coordination strength itself is not like a project production process is not that strong, but the coordination among different, let's say, different groups are still very, no, the whole process is very interactive and is still a strong coordination procedure. Okay, So that's the key point for work standard procedure. It's a little bit more standard. The process itself is a little bit more standardized. All right, and the customization level will be a little bit lower. All right, but still the standardization procedure itself is not that high, and the customization procedure, customization level itself is not that low. Okay, but compared to project production process, all right, the work standard type of the production process, the basically standardization process is a little bit high, and the customization level is a little bit low. All right, now, so for the manufacturing cell, this type of the production process, okay, as you can see, basically every area will more focus on one, specific, let's say, part or one specific component of this whole manufacturing process, right? So basically, the coordination among different group or among different area will be a little bit weaker, all right, will be a little weaker, and the standardization process itself will be stronger in the manufacturing cell. All right. So I will actually take you guys to look at basically this plot in order to illustrate the two key dimensions of different type of production process. But now let's just give you some sense about the key difference among different type of the production process. All right. So that's for the manufacturing cell. All right. As I said, the standardization procedure will be a little bit stronger compared to the first two type of the production process. All right. The customization procedure is a little bit lower, and because every area basically can just dedicate on that component or that part. They don't actually need those strong or those very intensive coordination among different groups. All right. So that's also is decided by the characteristic of the product itself. All right. So that's the first type, which is called manufacturing cell production process. All right. So the first one and the last one basically are two subtype of the assembly line production process. All right. So as you can see, for the assembly line production process, all right, we basically the work process are arranged according to the progressive steps by which the product is made. All right. And then similarly in the continuous process, basically we just the assembly line itself only the flow is continuous, such as with liquids. All right. Okay. So as you can see, no matter it's in assembly line production process or continuous process, all right, the whole manufacturing process itself is highly standardized. All right. So the coordination requirement in these two production processes is lowest among all different type of production process. All right, since actually the whole procedure itself can be very efficiently completed. Let's say by machines, as long as operators can monitor the whole procedure well. All right, so that's why here you can already feel that every different type of the production process, okay, let's say from at least two dimensions are different. All right, one dimension is basically the standardization requirement. All right, another dimension basically is the customization requirement. Okay, now let's move to this specific matrix. All right, the product process matrix. Okay, so actually I already talked about the key elements showing here within this matrix. Okay, so here, as I show here, right? So the vertical dimension basically the product standardization. All right. Of course, we know that if it's more standardized, then the customization level will be lower, right? So these are actually the two opposite way for the manufacturing process, and which also basically depends on the characteristic of the product itself, right? If this product is more like standardized the type of the product, all right, then of course we will use the production process that are more fitting for the standardization type of production process, right? But let's say for this product, this is a customized in this DIY design, then of course we should basically use the more customized production process. All right. So here we basically integrate no matter the customization or standardization into one dimension. okay, into one dimension. All right, and then another dimension add here is called product volume. All right, so actually, you can already imagine what is the relationship between standardization and volume in real business. Okay, let's say for a product, all right, if it is more standardized, then can you imagine what is the corresponding product volume? Will it become lower or will it become higher? Think about this. It will become higher, right? Because once it is more standardized, you don't actually need too much effort, going through the middle of the procedure in order to coordinate different points or to coordinate, different parts or different groups, right? So when this product is more standardized, normally the product volume will be higher. Okay, even for many different type of the product right now, since actually right now we have very efficient automated system. All right, so actually many things can be directly made by the machine itself, right? So as long as the machine doesn't have any mistake, as long as our people can monitor the whole procedure very well, if we just manufacture some their standard product, then machine can do it very efficiently. All right, so that's why here normally the relationship between standardization and the volume itself is negatively related. All right, so that's why you see we actually talk about these 5 different production processes, right? Project, work standard, manufacturing cell, assembly line, and the continuous process, right? These are 5 production processes that we just talked about and already covered most of the different type of the production process. All right, but you can see that actually here there's 5 different. We use 5 different let's say circle. All right, in order to present these 5 different production process, right? And you can see that all these 5 different production process are listed in this line, right? In this line, you see. Let's say for the project, all right, the project, you see the corresponding product volume itself normally will be low, but you see, and also the standardization dimension is also very low. Why? Because since the project production process really needs strong coordination, right? So this type of the product is not standardized product, it's customized product, right? That's why you see for the project type of the production process, the volume itself is low and is very customized. So on the other hand, basically it's a very little standardized production process, right? Because it's more customized. Okay, so this is a project. On the other side, all right, let's say for continuous process. So continuous process basically is the most standardized, production process. All right, it's fitting for those products is actually really standardized, and basically the machine and also the computer can already complete most of the job within this production process. All right, so that's why here this is called a continuous process, and you can see that the corresponding dimension for standardization itself is very high, right? It's a high standardized product, and of course for this type of the products, normally you cannot DIY, you cannot customize it. All right, so basically, especially for some, let's say, food or some let's say some clothes. All right, this type of the process is really fitting for those type of products. All right, and then here from the other dimension, if you look at for continuous process, you see that the product volume itself is very high. That's also very intuitive, right? Because you don't actually need to spend much time or spend much effort during the procedure in order to coordinate between different between different groups or between different, let's say, parts or components, right? So that's why here the product volume itself normally will be high. All right, so you see these are all different. This type of the production process itself are based on the characteristic of the products. Okay, and normally when the standardization level is low, all right, or equivalently we say when the customization level is high, then the product volume itself will be low. All right, and on the other hand, when the standardization level is high, all right, or equivalently we say when the customization level is low, then correspondingly the product volume itself will be high. Okay, but no matter which one, in order to make the whole procedure to be efficient, all right, normally these 5 different production process will list it like this pattern. All right. So you at least, all right, you have to, let's say, take one dimension very efficiently. All right. Let's say for this project type of the production process, since they're dealing with those very customized products, all right, it's very hard for them for this type of the production process to be, high volume production process, right? But at least, all right, you can make the, let's say, you can make the coordination itself very strong, the customization level very strong, very in order to basically satisfy customers, different type of needs. All right, so you may actually raise your price in order to compensate the low volume of this product. All right, so that's basically the key difference among these 5 different production process. Okay, you see from one dimension is a product volume, on the other dimension is called standardization. Okay, keep in mind what is the key difference here. All right, and what is basically the relationship between these 2 dimensions. They are negatively related. All right, now actually the following let's say 2 or 3 slides are still basically detailed talking about the production process. All right, like the first of all the project layout. All right, we say since we are more focused on the project itself, it's a customized process, right? So everything, every man and every facility, every equipment are focusing on this project. That's why here you see normally the product itself is remain at one place, and every different people and every different machine will come together and try to figure out this project very efficiently. All right. Here, the key characteristics that we require a high degree of task ordering. All right, and project layout may be developed by arranging materials accordingly to their assembly priority. All right, so you see that the whole procedure itself really needs high level of coordination and customization. All right, now the work standard. All right, as I said, you see within this plot, this pattern, this matrix is very useful for you to kind of differentiate different type of the production process. You see work standard is right here, right? So you see compared to products, the standardization level is a little bit lower, all right, and the product volume itself it can be a little bit higher, right? Because you see this is actually a very common approach to develop this type of the layout to arrange work standards in a way in order to optimize movement of materials, right? So compared to the project layout, right? So here, since the coordination level itself is not that intensive, right? So basically, we can build up a few different, let's say, work standard, all right? And every work standard will more focus on one type of the job or one type of component, but they are still, strongly connected with each other because, the customization level is still there. All right, it's not that as high as the project production process, but the within the work standard production process really needs some coordination level. All right, among different components, among different labors. All right, that's why here the work standard is having a relative high customization level and also has a lower product volume. All right, so these are the things actually we already talked about, and for more details please look at the textbook. Actually it already show you some very detailed explanation about it, but as I said, keep in mind what is the key difference among different type of production process. That's the most important thing. All right, and manufacturing cell, right, these are the another type of the production process. Okay, within this type of the production process, the whole procedure can be more automated. All right, and the product itself is more standardized. That's why the volume itself is also becoming higher. Okay, because you don't actually need much time to go through the whole procedure. All right, the whole procedure itself is automated in some extent. All right, and of course assembly line type of the product is most automated, is most standardized, and the volume itself will be higher. All right, so that's why here I also say that also another key important characteristic for this is that we design for some special purpose of building a product by going through a series of progressive steps. Okay, so later on, just in a second, we will focus on talking about the quantity methods within assembly line design. All right. So basically, for project layout, for work center, even for manufacturing cell, because actually there are a lot of customization procedure inside. So we were not focus on talking about the customization process, because the customization level itself is specific. It's a context specific. That's why actually for this whole thing, different projects, different products actually need a new design, need a new plan for the manufacturing process, right? But since the assembly line design itself is more structural and is more standard, all right, you also give us some chance to use some standard quantity methods in order to build up the bridge within this assembly line procedure in order to improve the whole efficiency during the procedure. All right. So that's why here, just in a second, we will talk about the specific detail. Talk about the quantity method in order to improve the assembly line design procedure. Okay. Now, let's move. Now, yeah, this is basically just a rough illustration about the applied illustration about the manufacturing cell development, right? So normally you see that we group parts into families that follow a common sequence of steps, all right? And basically, since they don't actually need too much coordination among each other, that's why they can basically group different parts into different family, and each family of the parts basically are will be done basically for, let's say, by a group of people, by a group of facility, and also by a group of equipment. Okay, the connection among different groups won't be that strong. All right, and after this group of the let's say parts already finished, it will move to the next part. Okay, we'll move to the next step. Okay, so you see everything showing here. Okay, as I show here within this specific picture, you see everything here is following a very strong sequence, right? Because after this one is finished, we move to this, and then move to this, and finally move to this, right? So there's a very strong structural pattern, among different, steps, okay? That's a very standard feature of the manufacturing cell development, okay? And also this feature will keep within the assembly line design procedure, okay? So, yeah, these are all things that I already talked about, okay? So, this is also basically just a picture about basically how the manufacturing cell, this type of the production process works, all right? And you see that we can separate into, different cells within the manufacturing process, and based on, let's say the feature or the characteristic of different parts, all right? And every group or every cell basically is just focusing on that part, focusing on that group of parts, all right? And then once it's finished, we move to some next step, and then until all the things were finished, and then they can combine with each other in order to get the finished products. Okay, so this is a very standard procedure. All right, so now let's move to the assembly line design. All right, so as I just said, the assembly line design itself is the most standardized manufacturing process, right? Because normally the steps of producing let's say for a certain finished product is specific. All right, so we should do, let's say we should do A before B, and then we need to do B, and then we need to do C, and then after we finish the task C, we can do D. So every step is already specified. We can even print out the manual for every step. All right, so there's no much room for coordination, because every sequential step is specified, and even is made by machine for all those steps. All right, so but there's still necessary or very important for us to use some quantitative methods to monitor the whole process, although this process itself is already very standardized. Okay, so we will use a very efficient and very important quantitative methods within this assembly line design procedure. Okay, and Okay, so in order to make the the whole procedure itself become more efficient. All right. Now, before we even jump into the quantitative methods here, I would like to basically talk about three key concepts within this whole assembly line design. All right. I think all of you should already look at the textbook and already see these three definitions. All right. First of all, it's called workstation cycle time. Okay. So in the assembly line design, although this is not work, this is different from the work standard type of the production process. Okay. But within, oh, sorry, let's say within the workstation, within the assembly line design, we also have the workstation. All right. And normally in the assembly line, we will have multiple workstation. Why we need to have multiple workstation? The reason is very simple because once you have the workstation, you can basically, let's say, use different workstation, okay, and let them work simultaneously, right? Then you will save some time, and then in the unit time, let's say in one day, you can produce more products in order to fit for the market demand. That's why we need the workstation, okay? But the workstation itself cannot be unlimited, right? Normally, because as we said within chapter 4, right, the capacity level itself is limited. You will have only have a number of equipment, have a number of facility, you have a number of the skilled people, right? So basically, all those things, all those peoples are limited. That's why here the workstation number itself is not unlimited. You have certain number of workstation, all right, and basically you try to use those workstation simultaneously in order to finally produce the product. Okay, but how we efficiently use those workstations, that's the key point in order to improve the whole efficiency of this assembly line design. All right, so workstation cycle time basically just a uniform. It's just a uniform time interval in which a moving conveyor passes a series of workstations. Okay, that's basically the workstation cycle time. All right, basically, let's say for a product, when you come to this workstation and then go out of from this workstation, all right, what is the specific time during this procedure? That's basically the workstation cycle time means. All right, very straightforward. All right, now assembly line balancing. All right, what is the assembly line balancing? All right, as I show here within the definition. All right, the assigning tasks to basically assembly line balancing is basically just assigning tasks to a series of workstations so that basically the required cycle time is met and the idle time is minimized. Okay, so what this balancing mean? The balancing basically is to use, first of all, we want to use a series workstation. Okay, we want to meet the required cycle time. Okay, that's the one aspect of the assembly line. But also, all right, we also we don't actually want to waste any time. Okay, we don't want to waste any workstation time. Okay, we have limited workstation. Okay, even if you have the ability to let's say introduce some new workstation in order for these products. All right, but we know that each time when we incur some new, let's say to introduce some new workstation, you will incur more cost. All right, so we really want to have some certain number of the workstation. All right, and fully use those workstation in order to fit for the market demand. Okay, so that's the balancing within the assembly line design. Okay, with certain number of the workstation, we can reach the final target and most efficiently use the time within the workstation. That's basically the key point here. All right, and the next one is called precedence relationship. Yes, so that's also very important. All right, as I said, within the assembly line type of the production process, right? Normally it's standardized. All right, and for produce and finish product, normally the step itself is already specified. All right, and with a very specific precedence relationship, means that let's say for this product, all right, it has let's say just 3 steps, A, B, and C. All right, and we know that we have to start from A, and then once we finish A step, and then we go to the B step, and then once we finish B step, we go to C step. Okay, so we cannot actually directly go to C step before we finish B, and also A step. Okay, so there's a precedence relationship between or even among different steps. You have to follow certain steps. Okay, so sometimes basically one step is a prerequisite of the next step. Okay, so normally this precedence relationship will be given from the context. All right, so if I test you, if I give you some question within exam related to assembly line design, I will, of course, I would give you some related information. All right, such that you will understand. Okay, so this step will be before that step, and when you basically build up the workstation for this type of problem. All right, now after we have a good sense about these three different definitions, now let's move to the calculation. All right, now before actually we jump into a specific application, I will use a very specific application for you guys to help you better understand about this assembly line design, because that's more intuitive and it's more applicable. All right, but before that, there's a few equations that we will use within that application. We will continue to talk about these equations. All right, but here let me give you some basic sense about what those concepts or what those equations means. All right, so first of all, when we do assembly line design, as I just said, we have to understand the sequential relationship. All right, also we call it the precedence relationship. This is normally given by the context. All right, and normally, all right, the information that I give to you will be described by the words. All right, but it's better to, or it's actually worthwhile for you to draw the corresponding relationship or the structure of those different steps. Um, let's say on the paper, all right, because that will give you a better sense about the whole structure of the different steps. Okay, so in the example that I will illustrate, I will also provide a diagram for you to better understand about that. You will figure out, oh, that's actually have some beneficial by plotting out the precedence diagram. It's actually very important. All right, so that's why here I also list here. All right. The required workstation cycle time. So the required workstation cycle time, as I said, all right. So the workstation cycle time basically is that, okay, let's say for this output, all right, when you start from start producing this product within this workstation until it's finished all the steps. Okay, in the end, become the finished product. What is the corresponding time that is necessary to produce? Okay, that's basically called required workstation cycle time. All right, you see that's basically C equals what? Is equals to production time per day divided by required output per day. What it means? The production time per day divided by required output per day. What is it? What is the corresponding unit for this equation? You see, there's a per day on the numerator. There's a per day in the denominator. All right. So if we calculate something here, let's say the number, let's say is 10. What is the unit? The unit will become production time divided by what? Required output. Means that for every output, what is the corresponding production time? Right? That's basically the required workstation cycle time. Very straightforward, right? So basically, what is the corresponding production time for every output? Okay, so if you are still a little bit confused about it, don't worry. I will use the example to illustrate. All right. Now, the next very important concept is basically the theoretical, okay, or more generally, we can say the ideal minimum number of the workstation that we really need for this production process. Okay, probably one workstation is not enough. Two may not be enough, or three even may not be enough. It's all depending on the context, right? But we also know that it's not more workstation is always better. That's not the case, right? Because if you introduce a new workstation, if you build up a new workstation, you actually incur some cost, right? That will cost you some money. So that's why here it's always worthwhile for us to know what is the ideal or what is the minimum number of workstation that theoretically we really need. All right. So in reality, all right, or in the specific planning, normally the workstation number will be higher than the specific number that we will calculate based on this equation. Okay, but we don't actually want the real number of workstation to be too high compared to this minimum number of workstation. Okay, because that will indicate that you do not efficiently use the current number of those workstations. Okay, so how to calculate this? Very simple. Use sum of the task times, right? Because for every production product, right, for every task, you probably would need some time to finish every task, okay, before it can move to the next step. All right, so the sum of the task times divided by the cycle time. What is cycle time? Which is exactly showing here, right? The C, which is the cycle time. So use the sum of task time divided by cycle time. All right, sum of task time divided by cycle time, that will give you the minimum number of workstation. Okay, again, this is just give you some sense about these two things, and we will use the example to illustrate. Don't worry too much about it. All right, and then we will select the primary rule to assign task to workstation and the second rule to break ties. Okay, so you may a little bit confused about what means by primary rule and what means by secondary rule. All right, and actually the key sense here is very straightforward. As I just said, in this assembly line design procedure, normally we will have some pre-specified, precedence relationship, right? So sometimes actually we may have the situation that there are let's say two different tasks in front of us, okay? But we are not sure which one we should do it first, okay? So in those type of situation, we probably need this rule, okay? The primary rule, okay, is to basically define, okay, or which is basically tells you this task should be assigned to which workstation, okay, or which task should get the priority, okay. So that's the primary rule. Why we need the primary rule, right? The primary rule basically is telling us, okay, now let's say we have some tasks in front of us, which one should get the priority, okay. So that's basically the primary rule tells, all right? And let's say if we use the primary rule and then we still cannot figure out which task, okay, we should get the priority. Let's say we have three different tasks, A, B, and C, all right? And then by using the primary rule, we figure out, okay, C should be after A and B, okay? But we still do not know whether we should let's say, get A priority or get B priority. At this time, we probably also need the secondary rule. Okay, so secondary rule basically is a supplemental rule. Okay, if the primary rule cannot help you differentiate, okay, which task should go first, probably second rule will give you some hint. Okay, will give you some clue about which task will get the priority. Okay, and in some extreme case, even if the second rule cannot give you some priority about which task should go first, then in those situations, normally you just pick up one of them randomly and do it prior to the other task. Okay, that probably won't actually affect too much. All right, so that's the key point showing here. All right, and also the primary rule or second rule, no matter which rule, the information, this piece of information will be given by the context. All right, so don't worry about it. And later on, in this example that we were talking about just in a second, all right, you will figure that actually, if we change a primary rule, or we change a second rule, all right, or we even just let's say in this specific example, we use one rule as the primary rule and another rule as the second rule. If we just switch the place, okay, if we use the second rule as the primary rule and the primary rule as the second rule, okay, the result can be totally different based on those rules. That's actually very intuitive, right? Because we are actually using this primary rule and secondary rule. We are following these rules to build up the workstation. All right. If we change any one of them, it may actually cause some consequence. Okay, cause some consequence. All right, now, yeah, our principle basically we assign different tasks. Okay, based on the rule that we just said. All right, we assign tasks to the first workstation. Okay, until this workstation cannot, take even one more task within this workstation. Okay, so let's say this workstation have let's say 50 seconds. All right, you already used 46 seconds of this workstation. Then how many seconds do you still left for this workstation? Only 4 seconds. All right. Suppose the next task really needs let's say 10 seconds, but for this workstation you only have 4 seconds. All right, you only have 4 seconds. But for the next task, in these 10 seconds, it means that okay, for this workstation, basically you cannot allow that additional task into this workstation. But how we can do for that additional workstation? For that additional task, we basically open another workstation in order to fit for it. All right, so that's basically the general principle. All right, and finally, we will put all of the tasks from the beginning to the end into different workstation. All right, and basically, you see this whole manufacturing procedure already put into different workstation, and that's basically helping us to improve the efficiency, right? And of course, after we finish all the things, we can evaluate and calculate the efficiency of the balance. And how to calculate this? You will figure out what is the sum of the test times. That will basically show to you. All right, you will actually got the actual number of the workstation. Okay, and then times the workstation cycle time. Okay, that will basically give you denominator. Use this numerator divided by the denominator. That will give you the total efficiency of the manufacturing system that you build up. Okay, so sometimes the efficiency may not be that high. You may actually change something within inside. All right, you may actually change the primary rule. You may change the second rule. You may switch these two rules. Right? Many things can change. Right? So that's why here, as I said, if we change some of the rule here, the result will be totally different. Okay? If we can improve the efficiency, that would be great. That would be great. All right. Now let's move to this example. All right. This is actually a very intuitive and very straightforward example. All right. Although you can see that a lot of information actually are included within this example, but don't worry about it. Let's go through this example. You'll figure out that's actually this type of the problem. If you understand this specific quantity method, it's not that hard, and but it will take some time to go through the specific procedure. And if you have any question, just let me know. All right. Now, let's say the context. All right. So the Model J wagon is to be assembled on a conveyor belt. All right. 500 wagons are required per day, and production time per day is 420 minutes. And assembly steps and times for the wagon are given. Find the balance that minimizes the number of workstations subject to cycle time and precedence constraints. Okay, so from this information context, actually you already know some of the very key information. All right. First of all, in every day, how many wagons you are gonna produce? You need to produce basically 500, right? So 500 wagons are required to produce every day. All right. And what is the production time per day? The production time per day is 420 minutes, right? 420 minutes, right? This is actually very intuitive, right? We cannot expect, people or the machine are working all the time in a day, right? So the production time per day is 420 minutes, okay? And we're trying to find the balance, the minimized number of workstations subject to cycle time and precedence constraints, all right? Remember that we also talk about the theoretical minimum number of workstations, but that's the idealistic situation, right? We can easily calculate this by just doing this division. But here, what we are trying to look at is the real number of workstation. Okay, the realistic minimum number of workstation subject to these constraints, basically. All right. Now let's look at some other information. These are all the information that we already provide by showing within this table. Okay, probably when you look at this table, you will see a lot of things showing here, all right? But actually the key structure and the key sense here is quite simple. Let's go through, everything showing with this table. All right, so first of all, let's say we're trying to produce a product, all right? This product here is the wagon, all right? For every wagon, it will go through every task showing here before it can become a finished, product, all right? So for every task, actually, you see within this table, it already shows you very, very specific information. Let's say for the test time, in order to complete A, it needs 45 seconds, all right? What does task mean, all right? I won't actually spend time to read this, but just go through all this description showing here, all right? So here, task A needs 45 seconds, and here's some description. And finally, this column is quite important, right? This basically tell you whether we need to complete some task before we actually start this task. Here, this is actually, there's no previous task, right? We sometimes we may use this symbol, sometimes we may use NA, which means not available, right? So here, basically it means, okay, A can be the first task, right? You don't actually need to you don't actually need to complete any other task before you start task A, right? So it can be actually shown at the beginning, all right? But if you look at B needs 11 seconds, but it needs to after A. So what it means that you have to first finish A, then you can start B, okay? So in this situation, you cannot directly start B. That's not correct, all right? So here, C is even after B. Means that, okay, you have to finish A and then B. After B, you can start C, okay? But look at D. D actually needs 50 seconds, and what is the corresponding precedence step? Now, right? There's no precedence step. Means that, okay, you can actually start D also, okay? You can also start D, all right? And you see E, it needs 50 seconds, and it has to start after D, okay, after D, all right? So you see all of the information related to the task symbol and also task time, also the precedence relationship is showing within this table, okay? Also for all of the tasks, all right? After you add it up, all of the tasks, if you complete a product, all right, you probably need 195 seconds, okay? So you see that if you directly use this table to, to describe the structure of this production process, it's a little bit hard, right? It's a little bit hard, but how to deal with it, okay? So that's why here we will introduce this called precedence diagram, okay? This precedence diagram itself is quite straightforward, okay? Basically, you just follow your logic, follow the fact and the precedence relationship, you can easily plot out this diagram, all right? The diagram, you see, basically what I show here, all right, is a standard diagram. As long as your key sense is exactly the same, you can actually put this branch here, okay? You basically draw here. You can put this upper branch here, okay? That's fine too, okay? But the key structure here, the sequence here should be the same, because this should be based on this sequence, all right, the precedence sequence. That's why the key sequence here, the key structure here should be exactly the same, all right? You can actually, by just looking at this table, okay, try to plot out the diagram yourself. Okay, that's actually very important, all right? Now, let me lead you guys to go through this diagram, okay? So A, there's no precedence step. That's why here, I plot A here, all right? And I also plot out the 45 seconds just above A, okay? Because this is a key information, that's why I do it, all right? Now, B is after A, that's why you see, starting from A, I basically draw an arrow, and then you see the next basically step is B, and it needs 11 seconds. It needs 11 seconds, okay? Very simple, right? Just follow this structure. Now, the next one's B. The next one's C. C is after B. How to plot it out? Very simple. B is after C. Then B out of an arrow, okay? M to C, and then this is 9 seconds, okay? And then what about D? You see, D has no precedence. That's why here you see D can also be you see the um, I plotted sorry, below D, right? You can actually plot, above D, above A, or some other place. That's fine, all right. But see, the key here, you see, in front of A, there's no connection, there's no error, right? In front of D as well, okay. So it already shows that A and D will be the potential starting task among all those different tasks, right? So here D is plot here, and then how about E? E is after D, right? E is after D, that's why E is here, all right? And no matter is, you see, F and G is after what? After C. F and G are after C, you see, that's why F and G after C, there's two errors, right? And HI is after what? H and I is after E. That's why here you plot H and I here after E, all right? And after you plot FG, H, and I, what happens? FG, HI is actually before what? Before J, okay? Before J. That's why you see all these four different tasks, okay, is actually aiming to J, okay? What it means? So it means that you can start to complete J only if F, G, H, and I, or this four tasks has been finished. Okay, has been finished. Okay, if you just finish F, no, you cannot start J. If you just finish FG, no, you cannot start J. If you finish FG and H, you cannot start J. You can only start J when F, G, H, I, all these different tasks have been finished. Then you can start J, because all these different steps are the preceding steps. Okay, all of them are necessary before you can start J. Keep that in mind. Okay. This is not that you just only finish one of them, you can start this. No, that's not correct. Okay, keep that in mind. Okay, now after J, okay, you can build up K, because you see J is precedent step for K. So that's how you basically plot out the whole diagram. Okay, the key inside here is very simple. No matter what kind of thing I change, right? You can even randomly, just change some of the precedent step here, and you can also write it down, as long as this is logical. All right. So here, these are the diagram. Okay. You see, compared to this one, compared to this plot, this diagram seems to be more clearer, right? It's more clearer. You already include all of the information, but also you see the let's say the seconds number, this information also show here, right? It's cleaner, it's clearer, and it's actually very simple. That's why here, normally when we go through this type of problem, we would suggest people to basically plot out the corresponding diagram first. Okay, people are more and more good at recognizing the pattern instead of looking at this piece of information. Okay, so that's why here we would recommend students, recommend even business people are when they deal with this type of the problem, just draw this diagram. That will help for them to look at the whole picture, look at the whole pattern. That's actually very important. All right. Now, we also basically need to calculate certain things before we can start to build up the workstation for different different tasks. All right. So first of all, as we show here, the first thing that we need to build up basically is the workstation cycle time. The workstation cycle time, right? So basically, for every output, what is the corresponding production time? It is necessary, in order to finish the output. Okay, what is the production time for the output? Okay, so here we need to produce 500 per day. Okay, the production time per day is 420 minutes. You can directly tell what is the workstation cycle time, right? Because the workstation cycle time is just the production time for every product, which is Wagon. How to calculate this? Very simple. This is 420 minutes, right? This is 420 minutes, right? So you see 420 minutes. All right. So here, here we just transform to seconds because we probably think seconds more efficient. Why we actually use seconds? There's a very important thing. Why we use second here? This is actually 420 minutes. Why we transform to seconds instead of minutes? The reason is that later on we will also compared to this test time, you see that what is a test time unit? The unit for test time is seconds. So basically, we need to kind of we need to match this unit, test my unit, all right, with the what? With this production time unit. Okay, that's why we transform everything to seconds. You can also transform everything to minutes, or you can even transform everything to hour. All right, but here we just use second uh, as the standard unit. Okay, and also in the homework, okay, make sure that you exactly understand what is the unit that this homework is looking at. All right. So if they are looking at second, you use second. If they use look at the minute, then you use minutes. Okay. So there's 420 minutes and times a 60 seconds per minute. It will give you the corresponding second. That's it. All right. And for every day, since we try to produce 500 based on this context, all right, 500 shown here. So that's how I'll basically give you what is a workstation. The workstation cycle time. The workstation cycle time is 50.4 seconds per wagon. All right, means that basically for every wagon, from the starting point of the production process until the end of it, okay, you need actually 50.4 seconds. Okay, 50.4 seconds. Okay, now if we look at this test time, A needs 45, B needs 11, C needs 9. All right. What is the total test time? It's 195 seconds, right? It's 195 seconds. Okay, now, for every wagon, okay, each workstation actually needs 50.4 seconds, okay? But, okay, for every product, okay, in order to complete the whole task, it needs 194 seconds. Okay, so basically 50.4 seconds per wagon is the requirement, is basically the target that we want to reach. Okay, but actually for every wagon, in order to produce it from the beginning to the end, if we do them sequentially, okay? If we do A, and then do B, and then do C, and then do D, and then do E, we do it sequentially, okay? Without any simultaneous move. Then we need actually 195 seconds in order to produce one product, okay? So it tells you if we do them sequentially, in total we need 195 seconds. But here, in order to fit for the market demand, in order to fit for the requirement, okay, every wagon only give you 50.4 seconds. How can you do that? How can you still reach the final target? You have to build up some workstation and then, yes, use the workstation simultaneously, right? Because let's say for one workstation, they are basically producing A and B or A and B and C, and then for some other workstation, they probably are doing job for D, E, and H, right? So in a certain period of time, all right, multiple workstation is doing their job. That's why here you can fit in this 195 seconds into a different number of 50.4 seconds. That's why here you use 195 seconds divide by 50.4 seconds. What this number means? What this number means? The 3.87. 3.87 means theoretically or idealistically, you really need to use 3.87 workstation simultaneously in order to finish your job. Okay, in order to finish your job. But we know that for workstation, it cannot be basically a decimal point value, right? It has to be an integer value. That's why here we run up to 4. Okay, so basically, if in this question, if I ask you what is workstation cycle time, this will be the workstation cycle time. Okay, if I ask you what is the minimum number of the workstations that we really need in order to fit for the requirement, we really need 4 workstations. That's it. Okay, so as long as you understand these things, it's actually very easy. All right, now let's continue. Now we already have this diagram. We also know that for every workstation, Okay, it can actually include 50.4 seconds. Okay, 50.4 seconds. Okay, and then we know that idealistic we probably need 4 workstations. But here we want to see, based on some rule, okay, what is the realistic number of the workstation that we really need? Okay, that's actually very important. Now, let's look at the corresponding um, table that I show here, which is actually very, very easy. All right, you see that here, this is A45, B11, C9, D50, right? I just basically just list all the things shown here. All right. And then what we are trying to do is basically uh, uh, put different tasks, okay, in order, all right, in order into different workstation. Okay. Now we start from the beginning, all right, and even before we do that, we have to point out what is the corresponding rule. Okay. The first primary rule is that basically when we have the, let's say we have, if we have to choose between two different tasks, all right, then we choose the task with a larger number of following tasks, okay, with a larger number of the following tasks, okay. That's the primary rule. What is the second rule? The second rule, actually this example also showing textbook, okay. You can also look at the textbook. Textbook already gives you very detailed explanation. Here, I give you a very detailed, explanation about it. And if you have any questions, just let me know. All right. So the primary rule is that it's based on the number of the following tasks. Okay, it's based on number of following tasks. The second rule basically is based on the longer operation time. Longer operation time. Now, keep those two rules in mind. All right. In this specific example, we use the number of the following tasks as the primary rule, the operation time as the basically second rule. Okay, we can of course we can change to some other rule, but within this context, this is the primary rule and second rule. It will give us some hint, give us some clue about which task will get the priority. Now that's from the start. If you just look at this diagram, okay, which task you can start at the beginning potentially. So potentially, can you start from B? No, because you have to do A before B. Can you start E? No, because you have to do D before you start E, right? Can you start A? Yes, you can start A. Can you start D? Yes, you can also start D. So potentially, no matter A or D, right? These two are the two tests that you can start with, right? Okay, so by just looking at this A or D, you can start A, you can start D. You cannot decide which one actually you start, right? In this kind of case, you use which rule? You first use the primary rule. Okay? Remember, what is the primary rule? The primary rule in this specific example is the number of the following text. All right? So the number of following text basically, which text actually has a larger number of the following text will get the priority. Okay? Which text has a larger number of the following tests will get the priority. Now, let's look at A. How many following tests have, okay, after A? B, C, F, G, J, and K. How many? 1, 2, 3, 4, 5, and 6. Okay, so from A to K, okay, basically there are 6 different tasks. That's why here you see the number of following tasks shown here is 6. That's why this number is 6. But if you look at D, how many? 1, 2, 3, 4, and 5. That's why you see D is basically 5. Here, in this table, I list all for all of the different tasks because later on some other tasks we have to differentiate. That's why I list all of them. Okay. Here you see that I list between A and B. A's following number of the following tasks is 6 and B's number of following tasks is 5. Which one should get the priority? A should get the priority, right? Because when we have the tie situation, we choose the larger number choose the task with the larger number of the following tasks in this specific example. All right, that's why here we start from A. All right, now A will get into this workstation 1. Okay, A will get into workstation All right. So you should remember that for every workstation, what is the corresponding cycle time? This is the first thing we calculate, which is 50.4. Keep this number in mind, right? 50.4 seconds is basically the workstation cycle time, okay? But for just A, how many seconds we need in order to complete A? 45 seconds, right? It's 45 seconds. So within the workstation 1, it gives you 50.4 seconds, right? And just A already used up what? 45 seconds. Then how many seconds you left? Use 50.4 minus this 45. You get this 5.4. That's why here this number 5.4 is showing here. All right. So 5.4 basically is the idle time. All right. Now let's say A is already finished. Okay. You see, after A is finished, which tasks can already be available? Say about this. After A finished, can we do B? Yes, of course you can do B, right? And can we do D? Say about this. Can we do D? Of course, you're right. You can do D also, because right now B and D are available. B and D are available, right? Now, same situation. When B and D, both of these two are available, we need to pick up one as a priority, right? How many? Okay, so first of all, by using the primary rule, how many following steps for B is 5? How many following steps for D is also 5? So basically, by just using the primary rule, we cannot differentiate which one, either B or D, should we get the priority. Then how we deal with it? We move to secondary rule. Okay, we move to secondary rule. In this second rule, in this specific example, the second rule basically is a longer operation time. All right, or we say basically it's a longer task time. Okay, from this diagram, can you tell which task has a longer operation time or longer task time? D has a longer time, right? D has a longer time because this is 11 seconds, this is 50 seconds. So that's why here, based on the second rule, okay, D get a priority. Okay, let me make it clear. Based on primary rule, we cannot differentiate B and D. That's why we move to the secondary rule in order to differentiate. All right, and by using the second rule, we find out that D get a priority. Okay, now we already know that for workstation workstation 1, we put A into it, we use 45 seconds, and there's a 5.4 seconds left. Okay, but how much seconds we need in order to complete D? It's 50 seconds. For workstation 1, you only have 5.4 seconds, but you need 50 seconds for this. How can you deal with that? How can you deal with that? You have to start another workstation. That's the reason here there's a station 2 for D. All right, there's a station 2. That's why here, you see, this is 50, right? What is the workstation cycle time? Again, 50.4. All right, that's why here 50.4 minus 50 is 0.4 idle. All right, 0.4 idle. Okay, now after you complete D, which tasks are available? B and also E. Okay, B and also E. Okay, so since B and E, both of them are available, which one get a priority? Still, we start from the primary rule. The primary rule is the following number of tasks. B has a 5 number of following tasks. E has 4, so B gets a priority. Okay? Still, B needs how many seconds? 11 seconds, right? B needs 11 seconds. Can we put B into station 2? No, because you only have 0.4 seconds for station 2. You have to still start another station, which is station 3. And you see B is at the beginning. Okay? So after B is finished, okay, in total we know that the workstation has 50.4 seconds, all right? And B used how many seconds? 11 seconds. Then how many seconds we left? Use 50.4 minus 11. That's why here this is 39.4, okay? 50.4 minus 11 is 39.4. That's the basically remaining units, okay? The remaining seconds for this workstation, okay? So here, after B is finished, which assignments are available? C and E, right? C and E. So still use the primary rule. How many tasks is after C? 1, 2, 3, 4. How many is after E? 1, 2, 3, 4. So you see, by using primary rule, we cannot differentiate between C and E. Okay, but by using the second rule, since E needs 15 seconds to finish, he gets the priority. All right, so within this context, okay, let me make it clear. All right, in this context, since we set primary rule as the higher number of following tasks and set the second rule as the longer operation time, that's why, okay, we follow this rule and we get this result. If we change to some other principle, let's say here, if we say the smaller operation time will get the priority, then suddenly everything changes, right? Everything changes. But here, since longer operation time gets a priority, then we should choose E, right? We should E will get a priority. That's why you see, okay, we know that E needs 15 seconds. Okay, can we put E also into station 3? Yes. Why? Because right now after B you still have 39.4 seconds, right? And E needs 15 seconds. You have enough time. That's why you put E into here. After complete E, use 39.4 minus 15. That will give you the result, which is 24.4. That's why here you see the left time is 24.4. All right. Now after B and E are after B, C, after BE, yes, B is finished. All right. And then which tests are available to us? C and what? H and I, right? C, H, and I, right? Because right now A, B, D, E already finished. C, H, and I, these three can be started, right? And for C, H, I, which gets a priority? Still use the primary rule, right? C, H, and I. C has the 4 following number task, right? That's why here C gets a priority. C used 9 seconds, right? So after complete C, how many seconds you still left within station 3? It will be 24.4 minus 9, which is 15.4. Very simple, right? Just 15.4. All right. Now, after complete C, which tests are available? F, G, H, I. All these 4 available. All right? All these 4 available. Now, by using primary rule, how many following tests for F, G, H, I? All these 4 have the 2, right? 2 following tests. We cannot use primary rule to differentiate. Now, by using the second rule, all these 4 are using 12 seconds. So you cannot use the second rule to differentiate. Then what we can do? Okay, if the context gives you, let's say, the third rule, you can of course use the third rule to differentiate. But without that, you just basically randomly pick up one and start. Okay, so that's why here I just use F here. Okay, but if you use H, if you use G, if you use I, that's all correct. All right, so here F needs 12 seconds and you have 15.4 seconds. That's why here you see you still have 3.4 seconds. And after this one is get down, which one is ready? J is ready or not? J is not ready. Why? J is ready only when F, G, H, I, all these 4 are down. Right now, only F is down. G, H, I are not down, right? Still, about G, H, I, as I just said, we cannot differentiate by using no matter primary rule or second rule, right? So that's why next step, we just randomly pick up one of them. Here I pick up the G, right? And then that's why here, G also needs 12 seconds. Can we put G into workstation 3? No, you cannot anymore, right? Because you only have 3.4 seconds for station 3. So G cannot put it into station 3. You have to start another station, which is station 4. And then it costs you 12 seconds. That's why here, by using 50.4 seconds minus this 12, that would be 38.4. Okay, that's the logic inside. Now, H will be the next one, right? H will be next one. Of course, I will be also here, right? Because you have to finish all these 4 before you can start J. That's why here, all of them actually are picked up randomly. That's why here I just start from F, G, and G, and then H and I. You can start to any one of these 4, all right? So here you see H, I, and after finish H, you use another 12 seconds. That's why 38.4 minus 12 will get you 26.8. And after you finish I, you basically continue to use another 12 seconds, which will give you 14.4 seconds left. All right. So after F, G, and H, I, or finish, you can start to do J. That's the thing, right? And then you can do J. And you see J will use up 8 seconds. How many seconds do you still have? Use 14.4 minus 8. That would be 6.4. All right, 6.4. All right. Now, there's only one thing here left, right? Which is K. Which is K. Can you put K into station 4? No, you cannot. You cannot because here you only have 6.4 idle. All right, 6.4. But for in order to complete K, it needs 9 seconds. So that's why here you see you have to start station 5. Start station 5. And so that's why here you see for station 5, you actually idle for a lot of seconds. Okay, that will cause some inefficiency. Okay, that's the whole picture showing here. Okay, I detailedly go through every task, every information, information shown here. All right, and as I said, okay, this is following some certain primary rule and second rule. If we, here's a quick exercise. All right, here a quick exercise you can practice. If we switch this primary to second rule and switch the second rule to the primary rule, how this result will change? Okay, you can use. Okay, you can still use this example to kind of have an exercise for it. All right, that's why I see workstation 1, workstation 2, workstation 3, and then workstation 4, and finally workstation 5. Okay, this is basically just a diagram to illustrate what we just said here. All right, very intuitively. Now, finally, we can also calculate the efficiency. Right, in total, for every product, actually it needs 195 seconds. If we do them, sequentially, it's 195 seconds, right? And you use how many workstations in total? In reality, you use 5, right? You use 5 in total. For every workstation, what is the corresponding workstation cycle time? It's 50.4, all right? So use 5 times 50.4. Basically, this is the corresponding, you can view it as the capacity level, right? So use 195 divided by the total capacity level. That will give you 0.77, or we say 77%, which basically indicates that the efficiency of your workstation itself in total will be 77%. It's not that bad, but you still have some distance away from 100%. So you can try to, as I said, you can try to switch this as the second rule and switch this as the primary rule and see whether the efficiency can improve or not. Okay, that's a very good exercise. Okay, now these are very intuitive and very straightforward example about the assembly line balancing type of the problem. All right, I hope you guys already understand it. Okay, if not, please let me know. All right, now yeah, reducing the test time requirements. Okay, so here I also list down different ways that can help us to reduce the test time requirements. Remember that in that example, all right, some of the workstation cycle time actually is in idle, right? And we do not actually efficiently use those, workstation cycle time. Uh, that actually will incur some cost. Remember that in that example, what is the idealistic number of workstation? It's 4, right? But in reality, how many we use? It's 5. So you see that there is some efficiency. Here, what it is here basically is give you some different ways that probably can help you to reduce some of the test time. Okay, maybe we can split the task, we can share the task, right? Because sometimes I'm busy, you are not that busy, we can share it, right? Then we can finish it in time, right? We can use the parallel workstation. That's exactly what we just said, right? We use 5 workstations and let them work simultaneously. That's how we basically fit for the market demand of our production requirement, right? That's exactly what we just said. And use a more skilled worker because he or she will be more efficient of doing things, and that's actually will be helpful from the production point of view. All right. Or if sometimes actually if the requirement is super high, is very high, people may actually work overtime. Or machine can also overtime, right? With some people's monitoring, all right. So that's also a way of reducing test time. Or we redesign the product, right? So maybe right now this in order to produce this product, the design itself is not that efficient. We can actually change something and make it more efficient. That's also possible. All right. Now here, basically, I just listed some diagram to help illustrate what is the basically the line layout can make the whole manufacturing process more flexible and more efficient. All right. So it's actually very intuitive. You see, within this diagram, all right, you see that every employee is basically standing at their place. Okay, and let's say one working process product is moving from here to here. Okay, so you see that basically, just have a quick imagine of this. All right, well, this product is at here. All right, only these two people can reach to it. Okay, and also, okay, probably only when product is reached to here, he can actually reach to it. When the product reach to here, he can actually reach to it. But let's say if many products reach to here, can he reach it? No, he cannot reach the product which is showing here, right? So actually, this is why this you see why this specific diagram actually has a problem, because they cannot share the task, right? They cannot share task. But let's say if we change the material flow like this, okay, the product is actually moving here from here to here, right? And then he will do something, she will also do something, all right? If she's doing faster, she may help him. If he's doing faster, he may help her, right? So they can actually work, they can have some coordination, they can help each other. That's actually making the whole procedure more effective and more efficient, all right? So that's basically one way of actually keeping and improving the material flow, okay? Now, so this is another diagram, all right? If this material is like a circle, it's like a closed circle for these people. And if this machine, let's say this material flow is also like another closed circle for another people, all right? So you see that only when the machine is going, in this diagram, only when when the product is going through this closed circle, this guy can handle it, right? Only, of course, only here, when this product is going in this closed circle, this guy can do it, okay? But it's very hard for them, to help each other, right? Because they're, basically they are working in a closed circle, and they cannot easily help each other, okay? They're not easily helping each other. But here, this is different. This is still a circle, but this is an open circle, okay? This guy is probably monitoring, more focused on this three, and this guy is probably more focused on this three. Okay? So when there's a lot of stuff showing here, or there's a lot of stuff showing here, this guy can help him, and this guy can help him. All right? So they can actually coordinate with each other. So that's why here, you see, an open circle is more efficient than a closed circle. Okay? That's why here, this is another way of improving the total efficiency by having more flexible line layouts. Okay, or in another situation, all right. So you see, if you do like this is like a straight line, all right. For this guy, okay, if let's say if she is very efficient, all right, she can finish all the things very quickly, okay. And let's say for this guy, if he is not that efficient, maybe he's just new within this production line, okay? It's very hard for her to help him because the distance showing here is quite long, right? It's quite long. So that's actually very difficult for her to help him, right? But here, let's say she's right here, all right? Let's say she's right here. She's more monitoring this too, all right? And let's say this new guy, he just come to this production line. He really needs some help, and actually, if she can do it quickly, she can easily go to this place and help him for some extent, right? You see, that's why when we switch from a straight line to a U shape, it's become more efficient, right? That's actually very intuitive and logical, right? So all the three basically plots showing here is to give you some sense about how the company, they will, change the pattern of the material flow in order to, make it more flexible. Okay, there are all those very good examples and are widely used within the real, operations management procedure. Okay, so to give you some quick sense about it. All right, more detailed things already included within textbook. All right, and again, I do require every one of you to look at the textbook and get a good sense about, those conceptual ideas, especially for the things that we emphasized within the videos. All right. So these are all the course material related to chapter 6. Okay. Thanks for watching and see you soon, guys.